Layers of the Earth. All right, so we have three major layers. There's a lot of what we would consider like sublayers, or a lot of the layers are divided up into multiple. The first one is the lithosphere, which is the crust, so the very outermost layer, plus the solid part of the mantle. So if you've studied layers of the Earth before, you might have studied them as like crust, mantle, and core. In chemistry, we study them as like lithosphere, which again is the crust plus the very upper solid part of the mantle, the asthenosphere, which is just under the mantle, and it's more of a liquid, like a very thick liquid. But it does have movement. So we get convection currents in there, which is the movement of that liquid. And then the third part would be the core. I don't know why it's not listed there. But the third part is the core, which is divided into the inner and outer core. You can see in this picture that the outer core is a liquid and then the inner core is a solid, which that is typical. That's what you've learned before. But as far as like crust and mantle, we're now going to call it lithosphere and asthenosphere. So again, lithosphere is like the solid part of the Earth, and then asthenosphere is like that liquid part where convection current occurs. The reason that's important is because that convection current is what makes like tectonic plates move, which is every time those plates are moving, they're like revealing new material or making new like rocks and sediment and stuff like that, which then contribute to all of our cycles on Earth. So how the Earth kind of works is sort of how we can exist here. Oil is found in the crust. Here's a nice little picture. It is very deep. We do have to drill down, but it is in the solid part of our Earth, the crust, the lithosphere. And that plate tectonics, like I said, the solid part is where we find oil. The liquid part, which is the asthenosphere, is what makes our plates move. And they're kind of named based on like where they are. So this African plate here, you guys can kind of see Africa. It's this gray line. And then the African plate is this black line that sort of surrounds that gray line. It almost kind of looks like the same shape, just larger. Same thing with like, if you come over here to the South American plate, you can see South America, and then you can see the plate kind of follow that general pattern. We have the Pacific plate, which is basically the Pacific Ocean, so forth. So we have the Earth is made of a bunch of plates. So even where there's water, you go down deep enough and you're going to hit solid eventually. And between each of these plates is where we get things like volcanoes or trenches. It just kind of depends on if the plates are moving together or moving apart. Or right here, this is where California is. You can kind of see there's like a little part that's like sticking out. So there's part of California that's on the Pacific plate, and then there's other parts that are on the North American plate, and we have a transverse fault there, which means it slides past each other. So those are the three kind of faults that happen in between the major plates. But why do plates move? It's because they're moving of the convection current underneath the lithosphere, the convection current that's happening in the asthenosphere. And what's happening is when we're down here in the Earth, we have really high pressure and really high heat. And the closer we get to the core, the hotter we get. That pushes all of the liquid part of that mantle of the asthenosphere up. And then as it gets closer to the surface, it cools down. And we know that hot stuff rises and cool stuff falls. So because of that, we get what we call a current. And that convection current, that spinning, is what moves those tectonic plates. Here's another good visualization of a convection current, this lava lamp here. You can see that the light, how a lava lamp works, is the light that's in the bottom of the lava lamp gets very hot and it heats the fluid. So once it reaches the bottom, it heats and it kind of rises. And then once it gets far enough away from that light at the bottom, it cools down. That's when it starts to fall. So that's kind of how a lava lamp works. Is hot rises, it cools down, and then begins to fall. That's sort of what you see here with these arrows. Again, hot is rising, hot molecules rising. It gets to the top where it's cold, cold molecules fall, and it creates a convection current. oil formation. So in between each of those plates, it's sort of how we get oil. Uh, that's not to say that oil can't occur in a middle of a plate. It can there as well. But when plates move, they trap, animals, fossils. Eventually even people. Anything that was like inorganic will eventually decompose, and over millions of years and a lot of pressure and a lot of heat, all of those once living animals become organisms that are now deteriorating over time, and eventually they get turned into oil. That's why we call them fossil fuels, is because it's like a fuel that came from a fossil. It does take millions of years, and they are formed by large amounts of tiny plants and animals. So in order for them to become a fossil fuel, they have to be under large amounts of heat and large amounts of pressure. So when tectonic plates are moving like underneath each other and other ones are moving over, so when they're going like towards each other, or even when they're spreading apart, right, they release a lot of heat. So high heat, high pressure is how we make fossil fuels. So because our plates move, those fossils can really get in there and they can get deep, and that's where we get all that high pressure. And then the closer it gets to the mantle, the hotter it's going to get, which is just going to create more fossil fuels.